Last video built the framework from the ground up. State your hypotheses, pick a test statistic, set a significance level, state the decision rule, calculate, and decide. Along the way, you met type 1 and type 2 errors, the trade-off between them, and the power of a test, all worked through on a single hypothesis test for one mean. This video applies that same framework to 4 more situations you'll actually meet on the exam. A single variance, the difference between 2 means, paired differences, and the difference between 2 variances, plus when a non-parametric test is the better tool for the job. These 4 sound like a lot of new formulas, but the shape never changes. Write out the 6 steps, and the only thing that's different is which statistic and which distribution Step 2 hands you. Think of it less as 4 new topics and more as one topic, asked 4 different ways. Start with variance. Every test so far asked about the average return, but sometimes what you actually care about isn't the average, it's how bumpy the ride is to get there. That's variance, and it gets its own test. Naxora's benchmark caps acceptable return variance at 16 in percent squared terms, about a 4% standard deviation. A fresh sample of 25 months shows Naxora's own variance at 20, noticeably higher. Is that a real breach of the cap or just sampling noise? The hypotheses. The null is that the true variance is no more than 16. The alternative is that it's greater, one-tailed. For a single variance, the test statistic is chi-square distributed with 24 degrees of freedom. Why a new distribution? And why does it look the way it does? Take a few deviations from the mean, say -3, +2, +4, square each one, and every result is positive, 9, 4, 16. It doesn't matter what sign you started with. That's the whole reason a variance estimate can never fall below 0, and why the chi-square distribution built from it trails off in a long right-hand tail instead of sitting in a symmetric bell. At 5% significance, the critical chi-square value is 36.415. The test statistic is a -1 times the sample variance divided by the hypothesized variance, 24 times 20, divided by 16, 30. 30 falls short of 36.415. Fail to reject. Naxora's higher sample variance isn't strong enough evidence on its own to call the cap breached. If instead you'd asked whether the variance simply differs from 16, not specifically whether it's greater, that's two-tailed. The same one-tailed versus two-tailed distinction from last video, just applied to a different statistic. Next, comparing 2 means from 2 independent samples. This is probably the single most common question in finance. Did this manager beat that one? Did this region outperform that one? Asked properly with the uncertainty accounted for instead of just eyeballing 2 numbers. 2 regional equity teams. Team A, 40 months, averaging 1.5% with a 3% standard deviation. Team B, 35 months, averaging 1.1% with a 2.8% standard deviation. Independent samples, both approximately normal, variances assumed equal. The hypotheses are the familiar shape. The null is that the 2 means are equal. The alternative is that they're not. Pooling only makes sense because the variances are assumed equal. Picture it like combining 2 overlapping piles of evidence about the same underlying volatility instead of trusting either team's smaller pile on its own. You get one better estimate built from all 73 data points together. If the variances weren't assumed equal, you'd need a messier formula, and the degrees of freedom wouldn't come out to a clean whole number either. Pool the variances first. 39 times 9 plus 34 times 7.84, divided by 73 degrees of freedom, a pooled variance of about 8.46. The t-statistic is the difference in means divided by the pooled standard error, 0.4 divided by 0.67, about 0.59. At 5% significance and 73 degrees of freedom, the critical value is about 1.993. 0.59 is nowhere close. Fail to reject. No significant difference between the teams. Now here's the distinction that trips up more candidates than almost anything else in this reading. Picture a clinical trial. Measuring blood pressure in 10 patients before a new drug and again after. That's paired the same 10 people twice. Now picture measuring blood pressure in one group of 10 patients and a completely different group of 10 patients. That's independent, no connection between who's in which group. Same number of measurements, completely different test. Look at the two side by side. Independent samples are two separate clusters. Nothing links a point in one group to any particular point in the other. Paired samples are matched, 1 to 1. Every point on one side has exactly one partner on the other. Back to strategies. 12 months of paired returns. Strategy A minus strategy B. The same 12 months for both strategies linked by date. Pooling variances the way you just did would throw away that link entirely. That link is worth more than it sounds. A paired test is more powerful than an independent samples test on the same data because pairing strips out whatever variation the two periods or the two portfolios share. The only variation left is the one you're actually testing. Market-wide noise that hit both strategies equally just cancels out. The mean difference across those 12 paired months is 0.30%, with a standard deviation of the differences of 0.95%. The hypotheses. The null is that the mean difference is 0. The alternative is that it isn't. Two-tailed, same shape as the very first Nexora test. The standard error of the mean difference is 0.95, divided by the square root of 12 dies, about 0.27. The t-statistic is 0.3, divided by 0.27 dal, about 1.09, with 11 degrees of freedom. The critical value at 5% is 2.201. 1.09 doesn't clear it. Failed to reject? No significant difference between the two strategies. Same answer. The confidence interval way. The 95% interval around that 0.30% mean difference runs from about negative 0.30% to 0.90%. It contains 0, which is exactly why you failed to reject. Last of the four, comparing two variances directly. Sometimes the question isn't which strategy earns more, it's which one is riskier. 25 months of one strategy show a variance of 18, 25 months of another show a variance of 10. Is one genuinely more volatile, or is this within normal variation? This is exactly the test a risk manager runs after a strategy change or a regime shift. Did volatility actually move, or does it just look that way in 25 months of noise? The null is that the two variances are equal. The alternative is that they're not, two-tailed again. By convention, the larger sample variance goes in the numerator, which keeps the F statistic at 1 or above and simplifies which table value you look up. The F statistic is really just asking one plain question. How many times bigger is one variance than the other? 18 over 10 is 1.8. The first strategy's variance is 1.8 times the second's. With 24 and 24 degrees of freedom, the two-tailed critical values at 5% are about 0.44 and 2.27. 1.8 sits inside that range. Failed to reject, the two variances aren't significantly different. Here's one for you, in the reading zone style. 4 short scenarios. 1. Comparing the variance of a single fund against a risk ceiling. 2. Comparing the variances of two different funds against each other. 3. Comparing the means of two funds run by different managers. Unrelated samples. 4. Comparing the same fund's returns before and after a manager change, month by month. Name the test for each. 1 is a test of a single variance, chi-square. 2 is a test of the difference in variances, the F-test. 3 is a test of the difference in means, independent samples, pooled T. 4 is a paired comparisons test, the same fund, matched by month. Every test so far assumes something, a normal population, or at least an approximately normal one, with parameters like a mean or a variance worth testing. When those assumptions don't hold, a non-parametric test steps in instead. That flexibility isn't free though. Non-parametric tests typically need more data to detect the same effect a parametric test would catch with less. Freedom from assumptions comes at the cost of some statistical power. Reach for 1 in 4 situations. The data doesn't meet distributional assumptions, a tiny sample from a badly skewed return series. There are real outliers. One wild return distorting the whole mean. The data is already in ranks, an analyst's best to worst ordering of 10 funds. Or the question itself isn't about a parameter at all, asking whether a sequence of up and down days is random, say, rather than asking about its mean. What ranks actually means in practice. Instead of using the returns themselves, 4%, 9%, -2%, you just use their order. First place, second place, third place. You throw away exactly how much bigger one is than another, but you keep which one is bigger. And that's often all a non-parametric test needs. For the tests you just learned, there's a non-parametric counterpart. In place of the independent samples t-test, the Mann-Whitney U-test, which ranks every observation from both samples together and compares the rank sums instead of the means directly. In place of the paired comparisons t-test, the Wilcoxon signed rank test, or more simply, the sign test. Your turn. A researcher has a sample of just 8 returns and has reason to believe the underlying population is heavily skewed, nothing close to normal. She wants to test whether the median return differs from 0. Parametric test or non-parametric? Non-parametric. A tiny sample from a skewed population is exactly the situation a t-test isn't built for. And testing a median, not a mean, points the same direction. Before the recap, here's the whole menu in one place. A single mean, or the difference between two means, t-distributed. A single variance, chi-square. The difference between two variances, f. Paired differences, still t, just applied to the differences instead of the raw values. Quick recap. Same 6 steps as always. 4 new statistics. Chi-square for a single variance, pool t for independent means, paired t for dependent samples, f for comparing two variances directly. Reach for a non-parametric test when the data doesn't meet distributional assumptions, has real outliers, comes in ranks, or the question isn't about a parameter at all. That closes out hypothesis testing. Next, in quantitative methods, parametric and non-parametric tests of independence, correlation, and categorical data that doesn't fit into a mean or a variance at all.